Good morning. We are going ahead with the next lecture. So this is quantification of crystalline solid. You will you will see that during the course of the lecture series, we initiated our discussion from the solution properties, and then slowly we are shifting our our attention to the solid state. The reason is that because the system we are focusing on, so that is the combination of both aqueous and the solid phase. You could see it is the iron oxide nanoparticle for biomedical application. Eventually, our aim is to understand that how iron oxide nanoparticle exists in the aqueous phase. It means that practically we have two components. The one is the aqueous phase, and other one is the solid phase. The solid phase exists in the crystalline form. So now it means that we must understand appropriately what is the meaning of the aqueous phase on which we are concentrating, and what are the physiochemical properties and how we can characterize the aqueous phase and its characteristic properties quantitatively. And the second aspect of this whole series of lectures is the solid state. We have arrived over here from the fundamentals of the aqueous phase, where we are quantifying the concentration scales in terms of molarity and molality, and eventually we have explained all the physical properties of the aqueous phase in terms of solute dissolves in the solvent. Now then, we slowly shifted to the microcrystalline phase that exists in the aqueous phase, and I told you that that is the synthesis of the nanoparticle. So for the synthesis of the nanoparticle, colloidal stability is required, and for the colloidal stability, we need to focus our attention on the amphiphilic molecules, and thereby we talk about the surface active molecules, or the surfactant, and their properties. Now we are going to combine all the different fundamental aspects on the objective of our GIAN program. So that is the iron oxide nanoparticle and their bioapplicability. So during the course of this information or the lecture series, now we will try to understand that what is the meaning of the solid phase and in which solid phase we are interested. So the solid phase in which we are interested, that is the crystalline solid. What is the meaning of the crystalline solid? I cannot directly take you to the iron oxide crystalline nanoparticle unless you understand what is the meaning of the crystal and what is the meaning of the solid state when we deal with the crystals. To begin with, first we need to differentiate between the crystalline solid and non-crystalline solid. The crystalline solids are those solid materials or those solids which have the long range order. What is the meaning for that? I mean to say that a crystal is in which the component of the crystal, so they have the repeated order in 3 dimensions along the x-axis, y-axis, and the z-axis. So if you take any fraction of the crystal, you will see that the component of the crystal's composition remains constant. So that is the meaning of the crystal. So it is a well-defined 3-dimensional order of the components which constitute the crystal. In contrast, amorphous solids, that is not the case. Though amorphous solid could be made up of only one kind of entities, those may be in the form of atoms, molecule, or any other form of entity. They do not have a long range order. The long range order means, suppose if I am saying that this is a solid substance, and you will see that if I am going to talk about this entity, it could be atom, molecule, or anything. So you will see if I am moving in any of the 3 dimensions, x, y, and z axis, you will see exactly the same pattern running across the 3 dimensions. That is not the case of the amorphous solid. So in the case of the amorphous solid, this kind of regular arrangement is disturbed immediately as you try to move either along the x-axis, y-axis, or the z-axis. So therefore, there is a contrasting difference between the crystalline and the amorphous solids, and the repeating units which repeat in 3 dimension, they are known as the unit cell, is the basic repeating structure of a crystalline solid. So in the case of amorphous solid, we do not have such kind of entity which could repeat in 3 dimension. But in the case of crystalline solid, so this is the case. Why we are more interested in crystalline solids? The reason is that the nanoparticle uh, on which we are interested, they may be the gold nanoparticle, silver nanoparticle, or iron oxide nanoparticle. They are all in the crystalline phase, not in the amorphous phase. It means the focus of our course is to deal with the nanoparticles, those possess exactly the crystalline phase rather than the amorphous phase. Uh, what is the advantage of the crystalline phase? Slowly, I'll explain that why we need the crystalline phase in comparison to the amorphous phase. Okay, going ahead with this, uh, this is the simple fundamental understanding that how many kinds of the unit cell exist. So you already know about this, but I'm just refreshing your idea. So it's a simple cubic, unit cell, tetragonal, orthorhombic, rhombohedral, and so on. But the unit cell, which we will try to understand appropriately, quantitatively, that is the cubic unit cell. So therefore, the first unit cell, simple cube or the cubic, our explanation in this lecture will focus only on the first unit cell. So these are the characteristic properties that what should be the edge length or the 3 dimensions of the unit cell, if they are equal or not, on the basis of that, as well as on the bond angles for all the 3 sides and how they vary from one unit cell to another unit cell. So on the basis of that, we name the unit cell. What is simple cubic unit cell? So simple cubic unit cell is uh, it is it is the arrangement of the atoms. You may consider there is a one layer of the atoms, and there is another layer of the atom where one atom is exactly placed on the layer of another atom, and this repeating unit repeats along the x-axis, y-axis, and the z-axis. Now, if you only pick the 8 atoms, because it is repeating in 3 dimension exactly in the same way, so therefore we are picking the smallest repeating unit. The smallest repeating unit is the eight atoms among any adjoining layers along the x-axis, y-axis, the z-axis. If you pick 8 atoms, 4 from the above layers, 4 from the lower layer, and concentrate on the center of the atom. This is the center of this atom. This is the center of this lower front atom center. And these are the corners, means these are the points which represent the center of the atoms which are on the behind these 2 atoms. So this is the center for this one is for this one, and the same is the story for the lower atoms. In this way, if I'm going to draw a line among all the centers of the 8 atoms, I'm going to produce a cube. You see that because all atoms are identical, so therefore all sides of the cube are identical. That is the length, width, and the height. They are all identical, and because they reside exactly one above the other and their sizes are equivalent, so therefore the bond angles as well, they are equivalent. So all bond angles are 90-degree bond angle. You assume that this cube is in the form of a sharp frame, razor sharp frame. And if I want to hold the sharp frame and snatch it out, then some part of each atom is going to be included in the cube, and that is the part of this atom, and this is for the this one, and this one for this one. And this way I mean to say that when I'm going to take out the frame, the cubic frame, that is a razor wire sharp, so it is going to slice each atom, and it will take away some part of the each atom. So it means that you would see there are 8 parts of 8 atoms. You see this part, this much part is included in the cube. Likewise this part, this part, this part, and same is the story for the lower 4 atoms. Now what is the meaning for this? We are trying to understand that what is the meaning of this. This is in fact the unit cell, right? The unit cell is the one that is repeating. So it means that this is the unit cell which repeats itself in 3 dimensions. Anything outside the unit cell we are not considering for the time being. As you could see, basically we have drawn the cube, we have drawn the unit cell by taking the center of each of the atom. So therefore, a greater amount of each atom resides outside the frame. But we have, because the definition of the crystalline solid is that there is a unit cell, and that unit cell repeats itself in all 3 dimensions. So therefore, exactly this is the unit cell which is repeating in the 3 dimension. How we can quantify this? See over here. We have a few more definitions. Means, do we have only one kind of this cubic structure? What if we can there could be another atom where there is a space? You see the intervening space, empty space over here or over here. That empty space can also be occupied by an atom. If that is the case, means you could see that if I'm going to place the atom over here, I mean to say that there is empty space. If I could insert the atom over here, then the definition of the unit cell changes. It still remains the cubic unit cell, but now the definition is body-centered cubic unit cell. In the body-centered means there is one full-fledged atom that is present in the center of the unit cell. That is why we name it body-centered cubic unit cell. What if, because we have the space over here, we have the space over here, likewise over here, likewise over here, front and back. Instead of inserting exactly over here only one atom, but we could insert more atoms in the interstitial spaces. Yes, we could do that. So therefore you would see this is one atom we have inserted over here, exactly the way over here. You see that this is the normal cube, the body-centered cube, when we added one atom in the center, and now there are spaces on the faces. This is the face of the cube. The face of the cube is this one. You see how many faces are there? There are 6 faces, 1, 2, 3, 4, and the front and the back. This is very, very important. Can you count the 6 faces of the cube? So cube has the 6 faces. If the cube possesses 6 faces, it means there is a possibility of 6 atoms can be introduced on each face. 1, 2, 3, 4, and this front and the back. So 6 atoms can be included. Now the same is the story for this one. If I'm going to take out this razor sharp frame out, and this is the unit cell structure for the simple cube, what would be the unit cell structure for the body center? So this would be the body center cubic unit structure. When I'm going to snatch out the frame, you see there is a full-fledged atom, and that atom is exactly in the center. Hence, that is not going to be affected when I'm going to take the frame out. Okay, now we need to quantify that how much area of this one atom, because that is exactly same in all the cases, how much the surface area of the atom is included in the unit cell. That we can calculate easily putting the atom, all the layers of the atom in three dimension. I have only shown one atom, but you could imagine there are atoms over here, here, above and below, and there are layers running above and below. So it means that if I'm going to erase the layers and only showing the frames, it means the atom that is at this position or this position or on this position, all these atoms all these atoms are in fact contributing to eight cubic structure, eight cubes. 1, 2, 3, 4, 5, and 4 is below. So 8 cubes. This corner in fact is the common corner that is being occupied by an atom, and that atom has embedded some portion of its surface area in 8 cubes, and therefore it is shared by the 8 cubes. So therefore when the area is shared by 8 cubes, so then we can say that one atom, so it is shared by 8 cubes. So therefore the surface area of 1/8 is included in one unit cell. So it is the unit cell. So 1/8 part of one atom is included in the unit cell. But that is the case when you have the simple cube. It is not the situation for all the other cubes like the body center or the face centered cubic structure, but this is only for the simple cube. Realized that there is one atom on the face of the cube. There is no issue for this because it is already inserted in the center of the cube. So therefore, the one full-fledged atom is already in the cube. But what is the area when an atom is going to be placed on the face, and how much area of it is going to be included in the unit cell? So you see, this is one cubic unit cell. There is another cubic unit cell. They have the common face. The common face because they are attached to one another. So therefore this face belongs to this as well as to this one. So therefore the atom that is possessing this face is half of this surface area is included in this unit cell and half in this unit cell. So therefore when the atom when the atom is placed at corner, which is also known as vertex, then 1/8 part of the atom is in the unit cell, and when the atom is on the face, side face, then half of the area is in the unit cell. Can you make out that? I don't need to explain it because the diagram itself is showing this. So you could see that there is half of the atom in this side and half of the atom on the other hand side. Okay. What is the meaning of this whole story? We are heading for the quantification. So therefore, we need to know that how much surface area of the atom is included in the unit cell. In three dimension, you could see this. There is a one cube, second, third, fourth. Likewise, there are four cube of the lower layer, and it means that this much part of the atom which is shared by 8 cubes is 1/8 that I have explained over here. And when the atom resides on the face, that is being shared among the two cubic unit cell. The half of the surface area is included in the unit cell. So for the body center, I have explained there is just one full-fledged atom in the unit cell. Now, if someone asked you that I can understand that there are 1/8 part of each atom included in the unit cell, then how much is the total surface area that is included in the unit cell. So you will find that the cube is you will find that cube has 8 vertices. There are 8 positions. So therefore there are 8 atoms. So the surface area included in unit cell. So there are 8 atoms, and each atom possesses 1/8 part. 1/8 part. Each atom possesses 1/8 part or includes 1/8 part in the unit cell. So therefore, I have total surface area equal to 1 atom. Is it okay? The total surface area, it means that the total surface area of all the 1/8 atom, 1, 2, 3, 4, 5, 6, 7, and 8, the total surface area of the atom that is embedded inside the simple cube is equivalent to 1 atom, right? The total surface area. So try to understand the language I'm using, because that is very, very important. The total surface area is equivalent to 1 atom. If somebody asks you, I have read somewhere that the unit cell possesses 1 atom, you will say, no, that is not correct, the way of explaining that. The unit cell cannot be made with just 1 atom. The surface area of 1 atom obviously can be included in the unit cell, and the unit cell can be made from the 1/8 part of 8 atoms equivalent to 1 atom. That is the meaning that the surface area is included for 1 atom. Okay, now how many atoms equivalent surface area is included in the unit cell of body-centered cube? So I have 8 atoms exactly weigh the simple cube, 1, 2, 3, 4, 5, 6, 7, 8, and there is 9th atom in the center. 9th atom in the center. So what I can do, it means that 8 atoms are equivalent to 1, equivalent to the surface area of 1 atom, plus there is 1 atom. So the total surface area is 2 atoms for body-centered cube, unit cell. Is it correct? So this is the body-centered unit cell. What is the situation for the face-centered cubic unit cell? And you see, there is none in the center, but all the six on the faces. So it means that I am still taking over here, plus 6. Each one is contributing half. So therefore, there are 3 atoms, surface area, plus the 1. So therefore, for face-centered cubic, 1 atom from here, from 4 atoms, 1/8 part, plus 3 atoms, total is 4 atoms. So 1 atom for the simple cube, 1 atom, body-centered cube, 2 atoms, and face-centered cube, 4 atoms. Is it okay? So, if someone asks you that which is the compact atomic arrangement in the crystal lattice, lattice means the crystal three-dimensional structure. We in solid state chemistry, we use the term lattice, crystal lattice, and you will be saying that the unit cell that contains greater number of a higher surface area equal to the greater number of atoms, that is the most compact arrangement. So therefore, among these three, the face-centered cubic geometry and the unit cell, so that has the maximum compact arrangement, and there are practically negligible amount of the interstitial spaces. And for the body-centered cube, still there are interstitial spaces, whereas In the case of simple cube, there are plenty of interspatial spaces. So in this way, we can differentiate. So this is the fundamental definition of the solid state, and we will only focus our attention on the cubic structure. And suppose if you ask me, this is the unit cell for a crystalline structure that has the cubic structure. And the straightforward question is that what is the unit cell structure for the crystalline gold nanoparticle, crystalline silver nanoparticle? The crystalline gold and the silver nanoparticle, they have the face-centered cubic geometry, right? And therefore, the arrangement in the gold atom in the unit cell which you will expect should be like this. Not like this or this, but so it's a very compact arrangement in the case of gold, silver, kind of noble metal nanoparticle. We are coming to the iron oxide nanoparticle. First, I'm going to explain this. Now, there is a way, suppose now we have realized that the face and the cubic unit cells are like this. Is there a way, suppose if I know the size of an atom that is making the unit cell, can I predict without performing the experimental measurement, can I predict that what is the size of the unit cell, what is the size of the cube? Or size of the cube means because all three sides of the cube, they are equivalent, so therefore I need to calculate the one side of the cube that is known as edge length. In the case of cube, right, this is the edge, right? This is the edge. This one is vertices. All the corners are the vertices, and this is edge. And this represents the length, one side of the cube. So therefore, this edge length is related to the radius of an atom. So without performing the measurement, if you know that a particular crystal is made up of this kind of atoms, and the size of the atom is, the radius of the atom is this much, you do not need to measure the XRD or other measurement to calculate the dimensions of the cube. Simply on the basis of quantitative treatment, you will be able to calculate the edge length or all the lengths of the three sides of the cube. So now in the case of simple cube, you see that the surface of the atom that is placed on this corner and the other atom that is placed on this corner, their surfaces, they are touching each other. So the surface of this and this, they touch over here. So therefore, the radius of this plus the radius of this, that is the edge length. I can say this is the edge length. I can say it is A because they are all equivalent, and that is equal to 2R. In the case of body-centered cube, that is not the case. In the case of body-centered cube, the surfaces which you see, they are touching over here, that is not the case. So there is a space over here. So therefore, you cannot use that formula right away to correlate between the radius of the atom and that of the edge length. And then you have to take another mathematical treatment, that is the we can draw a simple triangle with the 90-degree angle, and this one is hypotenuse. We know that this side of the triangle, the square of hypotenuse is equivalent to the square of the base and the plus the square of the other side, right? And here, what we can do, we can keep this as a triangle. This is one side, this is one side, they are equivalent, right? So the B square is equal to A plus A square. This is one triangle. We can have another triangle, and the triangle which we are drawing, so this is one side, or you may say the base of the triangle. This is the side of the triangle, but the hypotenuse in this case, that is running from this corner not to this corner. because both corner on one side of the face. This line is running from this corner to exactly to opposite, diagonally opposite corner. So therefore, it is running through the central atom. The atom which is in the center, this line is running through the central atom, reaching to the other opposite corner, right? So, and you will see the sides of all the atoms, the one this is touching the side of the atom that is placed in this center, and the side of the central atom is again touching over there. So this is R, this is 2R, or the d diameter of an atom, because the line is tracing or running through the atom from one side to another. So therefore it's 2R, and there is another R. So therefore what we can say is C square is A square plus B square, right? And now I have three A squares. I can add them, right? And I can substitute the B square over here. C square is equal to this, rearranging it. And so I have A related to the radius, edge length here, that is related to the radius through this formula. Now you will see that this formula is much complicated in comparison to this. Likewise, you can do it by drawing the triangle over here. So these are the relationship between the edge length and the radius. I mean to say that if you know the crystal structure of the unit cell of a crystalline solid, right? And if you know the radius of the atom, plug it over here, the value, radius of the atom, right way you can calculate the edge length. You can say that the unit cell edge length is this one. Likewise, the unit cell for the edge length for BCC, you can calculate like this. You can perform the simple calculation. Mathematically, that's not a big deal. For the gold atom, you can see that what should be the edge length for the gold nanoparticle FCC structure. So you'll be putting the radius of the gold atom over here, and you'll be able to calculate the edge length. Now, apart from this quantification, there is another relevant more quantitative parameters which we can calculate: mass and the volume. Suppose if somebody asks you, this is the unit cell for the face-centered cubic geometry like that of the gold nanoparticle. What is the total mass of the unit cell? Here we have not yet talked about the total mass. If we can calculate the total mass, obviously mass can be related to the volume through the density. Or if we have the volume and the mass, we can calculate that what is the density of the unit cell. So that is what I have shown it over here. Calculate the mass of a single aluminum unit cell. So mass of the entire aluminum unit cell. So for the color contrast, this atom has a different color from this atom, but in fact, as long as we are talking about the pure aluminum, all are the aluminum atoms. In North America, we call aluminum, and here in India, we call aluminium. Do not get confused. Aluminum and aluminium both are the same thing, only the way we name it. So it's a face-centered cubic geometry. So for the face-centered cubic geometry, we know there are 4 atoms, and it means that in order to calculate the mass of the 4 atoms, we need to multiply the mass with the formula mass. But you know that the formula mass is gram per mole. It is not the formula mass of one atom. It is the formula mass of 1 mole of an atom. The definition of a mole is the number of atoms equivalent to that of Avogadro's number. So it means that if you need to calculate the mass of a single atom, it means that you have to divide this formula mass of aluminum with the Avogadro's number per mole. You must cancel the unit with the unit, and eventually you should have the answer in grams. So this is the mass of a single atom. Since there are 4 multiplied by 4, this is the total mass of the unit cell. So what if we want to calculate the volume and the density, right? So here you see, calculate the density of potassium metal if the edge length of the body-centered cubic unit cell is 535 picometer. Okay, so it's 534 picometer. Edge length is provided. you have to calculate volume or the density. It is much straightforward to calculate the volume because all sides of the cube, they are equivalent. All sides of the cube, they are equivalent. So therefore, if I have to calculate the volume, simply I need the length of one side and I can take the cube and that would be the volume. And that is what over here. So edge length can be represented by A as I've shown it uh, over here, or it can be represented with L. The different textbook follow different way of depiction. So you don't need to get confused as long as it is representing, it's saying that it's the edge length, no matter it is being represented with A or L, it means that it is the edge length. So here it is represented with L, it is L not 1, right? So L cube, so it is in picometer, 10 to the power minus 12. Why we need to convert the units? The thing is the density is in centimeter cube, gram per centimeter cube or gram per ml. So therefore you have to convert the units. So you are converting the picometer into centimeters. So picometer into centimeter and then taking the cube and eventually this is the volume. You have the volume and now in order to calculate the density, you need the mass. The way you calculate the mass over here, the same way you are going to calculate the mass over here, but this is body-centered cube. Keep one thing in your mind that most of the exam questions, they will not tell you that how many atoms are included, how many atoms equivalent surface area is included in the unit cell for the simple cube, body-centered cube or face-centered cube. This you have to decide, right? So therefore, I mean to say that as you could see over here, it is saying the mass of a single aluminum unit cell, but it's not. It is saying that it exists in the FCC, that's the face-centered cell, saying that how many atoms, equivalent surface area is included in the unit cell of FCC. This you need to know that if it is one atom, four atom, or the two atoms. You got my point? So very important because most of the question will never tell you that how much surface area equivalent atoms included in the unit cell. So that is the case over here. That's what I'm saying, that you need to figure it out that how much is the surface area. It's two atoms, right? We've already talked about. So two atoms. So when you are calculating mass, you must be multiplying with 2 because the body center cubic unit cell not by the 4. It's not by 4. It must be with the 2 when you are dealing with the BCC body center cubic cell. Now you have volume and the mass and you can calculate ST. Make sure that all other units are cancelled, right? Coming back over here, so basically it's mass by the volume, so therefore no unit is going to be cancelled, but you must take care of the final units, gram centimeter cube. So therefore density must be represented with the conventional unit, so it is gram centimeter cube or gram. So that is the case. But here we can ask. So you should take that the density should be represented in gram centimeter cube. Uh, for that of the silver units. As I told you that gold and silver metallic crystalline pieces in any form in nanoparticle as well is the FCC unit cell. So therefore it is the same story over the same kind of calculation but with different number. So we have completed the basic definition of the crystal structure and the quantification. Look at all the slides or what we have gone through. If you have any question before I go ahead, because the next part is what I say. It is what we have till now understood or explained. So it is the self-test which we will go through in the next slides. you have any questions, you can ask me. Okay, realized we are heading to understand the crystal structure, unit cells of the ionic compounds, and how the unit cell of the ionic compound is related to the molecular formula. Now, somebody asked you that I cannot understand that when we write the molecular formula of oxygen O2, carbon dioxide CO2, it represents the single molecule, right? But when we write the molecular formula of sodium chloride, the salt which we use every day, and that is also represented with a single formula, and on the other hand, sodium chloride exists in a crystalline phase where sodium chloride is repeating itself in 3 dimensions. Then the answer is over here. Whenever the crystal structure you see for any salt, and the unit cell of a salt means, salt is a common term to be used for electrolyte, which is made up of 2 oppositely charged ions in any different ratio. Here you will see that cesium chloride, 1 cesium atom in the cationic form combines with the chlorine in the anionic form. Cesium chloride, the cesium cation, chloride anion, likewise the zinc sulfide, and then you see over here we have 2 fluorines for 1 calcium, right? Or 1 calcium cation, we have 2 fluoride ions. How can we derive the formula from the unit cell? It means that as we mentioned, as we have understood now, for any crystalline structure, the unit cell repeats itself. It means the unit cell should represent this formula, because this formula is repeating in 3 dimensions. So therefore, the unit cell must represent this formula. Okay. Now we will try to see if really the unit cell repeats this formula for the cesium chloride. Okay. So I have the unit cell is made by how many cesium cations are making the unit cell? How many? 8. Correct. So there are 8 cesium cations. How many chloride anions are making the unit cell? It's 1. Okay. Now, if you look at simple 8 to 1, you cannot figure out the formula. That's the confusing. If somebody say, no, cesium chloride unit cell is made by 8 cesium cations and 1 chloride, we cannot settle with the cesium chloride formula that is shown over here. Then, which is the correct way to represent that? So, it is not the 1 cation's total surface area that is included, right? So, how much that is? 1. So, it is 1/8 part. So, it means that 1 cesium cation is there. So, I can write 1, sorry. So, yeah, 1 cesium, and it, no, we should write it like this. And how many chloride? 1. That is exactly embedded in the center. and therefore its total surface area is equal to 1 atom or 1 A9. So therefore I can say, writing the chloride again 1. So when we have to write the formula for an ionic salt, make sure you understand that ionic salt always exists in the fully neutral state. So then you are not supposed to write the charges. So it is automatically understood that it is one positive charge, and there is one negative charge, and the overall charge is 0. So electrical neutrality is established. So therefore, when we have to write it, we will write cesium chloride. We will not write the subscript, right? It is automatically understood that one positive charge is balanced by one negative charge. That is the meaning of this formula. So this is the way we draw it. Now we have to prove that the zinc sulfide, this is the unit stand for zinc sulfide. So I give you 2 minutes or 2 or 3 minutes to prove that you really, the way you have come up with the cesium chloride formula, the same way you can come up with the zinc sulfide. Go ahead, please. Do it on your paper. How many sulfide ions are there? Where are they? And how many? You can take 2 minutes time, and then I can ask you. Okay, so how many zinc ions are there? There are 8 zinc ions at the vortices, and each one is contributing 1/8 part. So therefore, 1 ion is at the vortices. There are other 6 ions at the faces. You see the 6 ions? So this is the face. 1, 2, 3, 4. This one is the front face. This one is the back face. Cube has 6 faces. Okay, so therefore 6, 1/2 is contributed. So there are 3 ions total. Zinc. So that has 4 ions. Now we come to the sulfide ions. How many are there? All the gray balls. Gray balls 1, 2, 3, 4, 5. 4. Side, on the face, or outside? It is much easier to understand when the atom is exactly at the center, but when it's slightly, okay. Suppose if I that which geometry is this? Is it sp3? Which one is this? sp3. And is it octahedral? So tetrahedral, correct. So when it is, this one is tetrahedral. It means there are 4 connections. You see, for the tetrahedral, the central atom is connected to the 4th position tetrahedrally, and usually the bond angle is 109 degree. as you could see in the case of methane, right? And therefore, this position is on the corner, this position on the face, this position on this face, this position on this face. It means there is no way this atom or the ion could be away from any of the four positions, means exceeding the side of any of the four positions. It is somewhere in between the four positions. So therefore it is in the unit cell, right? So therefore how many? So there are four ions. Now you can place this zinc 4 subscript representing the four ions. Likewise sulfide 4 ions, and I have to depict it as a completely neutralized form. So it is 2 multiply, I can say 4 multiplied by plus 2 plus 4 multiplied by 2 minus exactly 0. So therefore I can think sulfide like this. You don't need to show the charges. You don't need to show how many atoms. Molecular formula for the sulfide that is repeating itself. The name of the unit cell is cubic. This is the common name. If somebody asks you what is the zinc blend, you may say because it's a common name for this salt unit structure, but the actual name is the cubic structure. Units. Potassium fluoride. So, again, how many calcium? Exactly the way we represented zinc. So, the same positions are occupied by calcium. So, at one atom, equivalent surface area for all the 8 vertices, there are 6 positions and contributing 3 atoms. So, therefore, I do need calcium 4 ions. Okay. Now, fluoride, how many ions? 8. 8. And what is the bonding or what is the geometry for the fluoride ion? Tetrahedral again, right? So therefore, inside the cubic structure, so therefore, you will say there are 8 ions. So I can say calcium 4, fluoride 8. Whenever you have something like this, the numbers which you can divide by the common factor, you must divide them to come to the undivided form. So therefore, it is calcium. If I'm going to divide with the 4, it is 1 by 2, right? So. Now, can we get the neutralization of a charge? See over here. It's 1 multiplied by plus 2 plus 2 multiplied by minus 1, right? So therefore, it is 2 minus 2, 0. Is it okay? Charge by taking 2 fluoride and taking 1 calcium, only then we can neutralize the charge. And that is why the formula is calcium fluoride. You do not need to show the charges. Okay. So, what I want to say that you can have more practices by picking more unit cells, structure for different ionic compounds from the internet, and you can practice by yourself. So we are done with the basics of the crystal structure, and we will see that how we can apply it to the focus our GIAN code. Try to see it. Now going ahead with this, How can we differentiate covalent crystal or the crystalline from that amorphous? The most prominent example is the diamond and graphite. Right? Both are made up of pure carbon atoms. The one is crystal, other one is graphite. Somebody can ask you, what is the problem? Diamond is clear crystal, graphite is not, right? And where is the problem? So can you tell me that what is the geometry for the carbon in diamond and what is in the case of graphite? Tetrahedral in diamond and in graphite. Okay, this is methane, this is ammonia. What is the geometry for the methane? What is for ammonia? No. I'm saying what is the bonding structure, Lewis structure for that of ammonia? Pyramid is the shape, not the geometry. When we say geometry, it means that you have to name the geometry. So tetrahedral is the right, and likewise for ammonia, what is the geometry? Again tetrahedral. Which one? Okay. Why we have still tetrahedral in both cases? There is no bonded position. Here you have the bonded position. But when we do not have the bonded position, can't be it sp2 because there are three connections, there are three bonds. So it means that the central atom, whenever it is possessing the lone pair, 1, 2, the lone pairs are counted as the bond positions, right? Do not exclude them. So it means that there is a fourth position available, though it is not occupied, and that is why still it is sp3. But here, do you see something like this or not? Do you see the lone pair on the carbon in the case of graphite? No. So, it is sp2 hybridization. It's a triangular planar. You see the triangular planar? That is the shape of the molecule, right? This one is tetrahedral, and the bond angle. What is the bond angle for the triangular planar? How much? 120, correct. So, in fact, these are the layers, and as you might be remembering, when there is sp2, right, and there's a fourth position which exists in the form of pi bond, right? So that is what over here. The layer, one layer below, and there is another layer, so they slide one above the other, so therefore these positions are not fixed, right? When these layered positions are not fixed, they slide one above the other, so therefore you cannot have a crystal structure in the form of crystalline form. It is the amorphous. Okay. So this is the right way, the correct way of evaluating it. Molecular crystals, you know, they are soft like sugar is a molecular crystal, right? So here we were talking about the most of the time the ionic crystals here. And then it's a metallic crystal. So metallic crystal, all transition metal. So there is a mobile electron. See, they are the fixed positions, right? And these positions indicate gold. So that is the FCC structure. So this is the comparative physiochemical properties, ionic, covalent, molecular, and the metallic, and the general properties and the examples are over here if you want to compare them. I'll take another few minutes. So glass is also, the one glass it is not the condition that if the light runs through the solid substance and that could be a crystal. That is not the condition, right? Light can run through the window glass, but window glass is not a crystal. It is amorphous, right? So therefore that is not a condition. But most of the crystalline substances, you can see through them, but that is not a blanket statement. Okay, so in the case of glass silicon oxide, when it's quartz, that is on the fixed position, only then it's crystal. Otherwise, the normal glass is not a crystal. So in conclusion, what we have learned today, the difference between crystalline and amorphous solids, that was the main discussion. We started from, our focus was on the crystalline solid, and then the crystalline solids, we wanted to quantify them by defining the unit cell. Our focus was on the cubic unit cell, and because the cubic unit cell is one of the most prominent, important unit cells that is possessed by the gold and the silver nanoparticles. And then we talk about the quantification of the solid, I mean density of the unit cell, the mass of the unit cell, and all other properties, how we can relate the unit cell with the radius of an atom. Thank you so much for your attention, and if you have any questions. Good afternoon. We are going ahead with the next one, material chemistry of biointerfaces. Realize some of the fundamental information regarding the crystal structure of the solid state. Now we will keep our attention on the material chemistry, particularly of the gold nanoparticle, the silver nanoparticle, how we can control the shape and structure of the nanoparticle, and how we can apply them or how we can use them for different kinds of applications. At the end, we will talk about the biointerface, but I'll explain that what is the meaning of the chemistry. This I have already explained that what is the definition of the nanoscience. So when we deal with at least one dimension that resides in the scale of nanometer, so then one dimension of any form of a matter, when it resides somewhere, one to, so we call that object as nanoparticle. So in the nanometer scale, our naked eye cannot pinpoint or focus on single particle. Why we need this? In fact, because the reason is we have just one planet, and with the materialistic life we have, so therefore, in order to accommodate all humankind on the limited space of the, we want that the objects which we are using, so they should be much small enough with much greater facilities, and, so that we can keep them wherever we want, rather occupying a much bigger space. So nature is not going to increase the dimensions of human beings. You cannot expect that after maybe 50 or 100 years you will have all human beings of more than 7 feet. That is not going to happen. So therefore, around this size, 5 to 6 feet, and the space on this planet will also remain like this. But the devices which we want, we are using, those devices we want, they should perform much more applications, much more facilities. Earlier, when the cell phone technology started, you are only able to phone call or to receive the phone call. You know, the cell phone is a kind of a small computer thing. So it means that it's basically the components which are included in the cell phone, their size. You see the size of the forceps, right? And you see the component in the electronic structure. So therefore, in order to this component, you need even much smaller component to whom you can receive even. So therefore, here the technology you are going to use, so that is the nanotechnology. Likewise, in the healthcare, your arteries, they are not going to be bigger in future. The size will remain the same. Earlier, cleaning the arteries from the cholesterol, you are using the drugs, but in future, obviously, probably the drugs are going to be the obsolete kind of medical help, and you will have the smart devices or the smart robot structure. So those can be introduced into the bloodstream, and they slowly, simply by scratching or moving, and they can remove the cholesterol, and you don't need to take any kind of medicine. So therefore, these mechanical objects, so they can perform your all kind of medical activities. So bottom line, in order to make a smaller device, you need even much smaller components, and those much smaller components require nanotechnology. So that is the application of the nanomaterials. We will see how can we perform some of the simple applications for the nanomaterial in the healthcare, but at the same time, it's not the glamour of the nanotechnology which I want to show it over here, but at the same time I just want to show that the nanomaterials are highly toxic and how we can avoid the toxicity of nanomaterial. Exactly the way every medicine has the side effect and how you have to avoid the side effect. Similarly, when we have the mechanical devices inserted in the human body to perform certain medical activities, so there are always the side effects, the toxicity, how we can avoid that. So nanotechnology, in fact, is not limited to the people who have the chemistry background. Nanotechnology is the technology that is being adopted by every walk of life. You will see the engineer, mechanical, material engineer, so they are also using the nanotechnology. Life sciences, chemistry, biology, they use nanotechnology. Computer science, information, electrical engineering, so they all use nanotechnology. So nanotechnology, the word nanotechnology, in fact, refers to the kind of protocols, devices, all those objects which we are going to use for the benefit of the humankind. So those objects possessing the tiny components, in order to compose those tiny components, we need a technology whom we call nanotechnology, because that technology works at the nanoscale. This is the kind of research that is going on in the United States. You will say most of the places where the amount of research is devoted to nanotechnology. University of California is much ahead in comparison to other well-known places, North Carolina, University of Illinois, New York, University of Michigan, Northwestern University. So the people over here, they are producing excellent research. University of Texas, Houston, and the Rice University. So they are in Texas. They are doing excellent research work. Rice University is over here. So I mean to say that this is not only the places in North America where the people are working in nanotechnologies, nanomaterial, but apart from this, there are other places all over the planet. In India also people are doing excellent job. They are doing very good research work, and even there are some places in North India like the National Institute of Technology, probably in Mohali, I don't know what is the correct name of that. So they are doing excellent research work. So there are several places in India as well. So I mean to say the amount of research work that is being promoted, so there are many places in the United States, obviously many people are working in that direction. This you already learned that there are two ways to produce the nanomaterial, top down and bottom up. So I have already explained that. Now, the thing which I want to explain, once we have realized the crystal structure, the unit structure, now we will try to see that how the crystal is grown into a well-defined shape. So when the nanoparticle is being grown, it is being the growth or the crystal structure or the nucleation of the nanoparticle is controlled. So you can achieve a specific shape. That shape could be a rod, bar, or a wire. It could be a cube. It could be a prism, icosahedral, or a sphere. This all depends on the application that requires that particular shape. So you cannot simply pick any shape and to use it for any kind of application. So the shape is always specific to a particular kind of application. So I'll explain how that is. In order to achieve a shape, you have to control the crystal growth. Now you know that the crystal growth is controlled by the unit cell. We define the crystal growth, a particular crystal structure for the unit cell. So you may say that this is a tiny gold nanoparticle. This is a bigger gold nanoparticle. Here only 13 atoms are involved, 55, 147 or 293 atoms are involved, or any number over here in terms of percentage. But the arrangement of the unit cell is always face-centered to geometry. The unit cell which I have explained in the previous lecture. So that will be the unit cell no matter what is the size of the crystal. A tiny size of the crystal or a much bigger size of the crystal. So eventually when the crystal grows, there are different ways we can control the growth. And I have already shown you this slide, This is the simple synthesis of the gold nanoparticle. So by using the the reducing agent, so we can produce atom and then we allow them to grow in the presence of surfactant stabilizing agent. And what kind of gold nanoparticle we could see. So these images are showing that if we control the crystal growth, we could have the cubes. You see the cubes? Clear cube. It is not the one unit cell. You don't need to get it confused. It's not the one. It is the shape of the crystal. Right? So this crystal contains of millions or millions repeating unit cell. Right? So for the gold, if this is the cube of the gold, so it means that the unit cell remains the face-centered cubic unit cell. So it could be like this, it could be like prism. As I told you, when you have to measure the dimension of the size of the particle, always keep your attention on the scale bar. So it means that the size of this cube is, one side of the cube is close to or slightly greater than the 100 nanometer. And here is the prism, then this is the hexagonal structure, and it's a roughly spherical wires, rise, this is rise, this is also rods, you can say, but these are the bars, clear bars, or the rods. Bars, the bars, the width is much greater than the rod, so we usually say this as a bar. So I mean to say that these are the different kinds of the shapes of the nanoparticle. The shape of the nanoparticle is complementary to the color. So a particular kind of a nanoparticle, shape and size of the nanoparticle, provides the color of the solution. Because when the nanoparticle, the electron cloud of the transition metal, so that interacts with the wavefront, so thereby there is the absorption of the photons, and the question is that the absorption of the energy that is being used while interacting the electron cloud with the wavefront, and where it resides, in which wavelength, in the visible region. So the wavelength in the region wherever it resides, accordingly you see the color of the solution. So as the size of the sphere of the gold nanoparticle increases, you see the color change. It's a bright red, it's slightly changing slowly to purple and the light blue color. And now the most obvious question is that, so this color is only because of the presence of these tiny particles, those are suspended in the colloidal solution. So suppose if I have to use this for any kind of application, this suspension must be a stable suspension. If the particles are going to settle, I cannot use them. Right? So therefore, this is the condition for the application, that that the suspension must be stable. Suppose if I want to use this suspension for a kind of application, it means that every time when I produce this suspension should have the size and the shape of this particle. Okay. Now the thing is that because the shape and size of the particle, which is over here, is providing me the maximum or the optimum results for a particular application. Now let's simply take the gold dust. This is gold dust that is obtained by grinding the gold. And can I simply put it in water? Can't I obtain a solution like this? Somebody who is a layman, who is not very clear about the colloidal stabilization, can ask you that rather than putting so much stress in the synthesis of the gold nanoparticle over here producing the colloidal suspension, you take a small piece of gold and grind it to make it a dust, and simply put the dust in pure water. And why can't you have a suspension like the gold nanoparticle? The problem is that you cannot do that. By grinding it, the first thing is you cannot reach to the nanometer scale. You can have a larger particle, and when you have the larger particle, another thing is by grinding, you cannot control the shape of the particle. You can, somewhere you can control the size, maybe, but you cannot control the shape of the particle when you are grinding it, right? So therefore, the shape of the particle is, if somebody asks you why the shape is important, because you see that the shape is also representing the color of the solution. We will explain that, as well as the application where we need that particular kind of shape for the gold to the silver nanoparticle. So, you see now, if your sample is giving the mixture of all the shapes, that is not a good sample for a particular kind of application. You do not know how the gold nanorod is interacting or being implemented for that particular kind of application, or the wire is going to show its effect for that particular kind of application, or the assembly small nanoparticle of roughly spherical shape. If you want to really understand that how the gold nanoparticle is showing its applicability, then the shape must be uniform. That is the reason when you are producing the sample of any of the nanomaterial, so the shape of that sample particles must be consistent. So this slide I showed you previously, and here I am simply saying that, so how can you control the shape? It is all, means obvious question is now I have shown you very different shapes. So it is much easier to understand that how I can control the shape where the gold nanoparticle can be transformed into ribbon or a wire. Right, there are other complicated shapes, but that is not easier to understand how we can control them. So, but here, if you passivate some of the crystal plane and you leave the one, that can be used and transform the nucleating center into a particular direction, the growth, to direct the growth into particular direction. So that would lead to a particular growth. So as you could see that if I'm going to allow the nucleation to happen only at this crystal plane, then the growth will grow in this direction and the nucleating center will convert into nanowire. What is the applicability for this? So you see over the applicability, we are going to, this I have already shown you, this slide as well. So we usually perform the seed growth method in order to produce the ribbons. But the bottom line question is how to use them, because here we are talking about the applications. So the nanowire which we produce for the gold or the silver, for the metallic nanowires, people are using them to cure Parkinson, Alzheimer diseases, particularly those are induced by the brain disorder, right? So still we do not have a clear kind of a medicine which could control these critical illnesses. So therefore, the other techniques based on the nanotechnology have been introduced. So if you inject some sort of a medicine, if you want, or certainly you want to give the electrical impulses to the brain, right, you can inject the sample of the nanowire into the brain over here, and this is the image, and then you can give the electrical impulses, because the metal wire is more prone for the electrical effect, and therefore it can stimulate some of the brain dead cell and it can regenerate them. So this is the idea behind that. So in this way, the transmission of the electrical signals among the brain cells can be reactivated, and particularly that is required in order to cure such kind of illnesses. Other thing is that you can have the nanowire technology to be embedded in some kind of a device, and that can produce the electric impulses, and it can be implanted in the brain. Most of these studies are performed with the animals, so I'm not sure that if now they have started with the real test for the human beings, but for the animals they have been doing it from last several years, and results are there in the form of publications. So this is the application for you may say nanowire, nanoribbon. So similarly we have the applications for the spherical nanoparticle, prismatic shape nanoparticle, or the cubic nanoparticle. So there are plenty of applications, but I have to show you just one or two. Likewise, I have not yet come to the magnetic nanoparticle. I will be coming eventually, I think probably in the next lecture tomorrow sometime. So this slide I'll show and I'll explain in detail. So here you have the magnetic nanoparticle, the meaning for, you see this black solution, completely homogeneous solution. When in place the magnet close to this, all particles are attracted to the magnet. It means that the particle itself, themselves, behave like the tiny magnets. So when in place the magnet, so all particles are attracted toward the magnet, and you have the clear water. This is a purified solution. There are only magnetic nanoparticles suspended in water. And when I pull the magnetic nanoparticle by using the magnet, there is a pure water over here. Can I use them? Yes, it is possible. How we can use them? Okay, they could be in any form. I'll show you. Most of the time they are in this shapes. Those are practically, you may say, we call them, it's not roughly spherical shape, but we call them faceted nanoparticle. The nanoparticle having particular faces, crystalline faces. They could be in cubic shape or the other geometries. Rarely they are in the rod shape. So they are the rods of the iron oxide. So you can synthesize rods as well if you want, but most of the applications of the iron oxide nanoparticles are performed with roughly spherical particles like this. How can we use them? The best way is we have the pollutant in the contaminated water. We add magnetic nanoparticle, those are functionalized. So the magnetic nanoparticle entrap the pollutants. We place the magnet. In this way, the nanoparticle, and now you have less amount of pollutant, or you can entirely remove the pollutant. So you can purify the contaminated water. Similarly, over here, you see, this is the study of a Chinese professor. So here, we have a sponge, and this sponge is in fact embedded with magnetic nanoparticles. So this sponge, when we place in the contaminated water with the blue color of the dye, you may say, right, the sponge is going to absorb all dye, and then how to collect these sponge particles, because they contain iron oxide nanoparticle or magnetized. Simply you place the magnet and collectively you can remove that, and your contaminated water is now purified. So in this way, I mean to say that there are plenty of applications you can choose. I would suggest you that in National Institute of Technology and NIT here, some of the most important journals from American Chemical Society, elsewhere they are available. So therefore, you should have the keywords like applications of the gold nanoparticle, and you will have lists of nanoparticle publications. You don't need to fully understand the publication. I'll simply say how to become a researcher. You cannot become a researcher in overnight or fortnight. It takes years, right? So therefore, what is the right path to begin with? The right path to start with researching is, so the field in which you are interested, whatsoever is gold nanoparticle, silver nanoparticle, iron oxide nanoparticle, first simply pull down the related publications, take the printout. You may read them on the computer, but I feel that when you have the hard copy in front of you, you will have a better grasp of understanding rather than simply reading on the screen, right? So read them. So don't expect that you are going to understand everything. It never happens, right? Because this is not your work, somebody else's work. So therefore, there is no way you are going to grasp anything. You may expect that, probably I'm not a good scientist, or I may not be having the appropriate understanding because I can't understand. That is not the thing. You cannot understand everything, right? So therefore, you should accept that only the part which you can understand. So whatsoever is, even if a tiny paragraph, that is enough in the beginning. Likewise, you should download the publication related to application, maybe application of cleaning the contaminated water. There are plenty of publications related to the cleaning of contaminated water by the magnetic nanoparticle. And you will see there are wonderful ways to clean the contaminated water by using the magnetic nanoparticle. And you can also download and see the applications, the medical applications extended by the gold nanoparticle in the in curing the critical illnesses. So that also you can read, and you will be able to understand how the nanoparticles are being used in a particular direction. So that is the way you start reading and putting and generating your interest in a particular direction and start thinking in that direction. Slowly, slowly you start working in that direction, and slowly, slowly it will help you to understand each and everything. That is the way one can become a scientist. Going ahead now, so there is another most important thing is target drug release. Actually, this application is very common, and you might be reading it frequently, right? And how it happens, and how how the nanoparticles are being used for this kind of treatment. You know, when you go to, I would say, what we call non-conventional doctor, a desi doctor who is not equipped with full degree, MBBS or the specialization. So he or she will say, okay, if you have a problem, take milk with the haldi and all those things, and everything is going to be all right. So no doubt haldi is excellent way of treating several things, but one thing you have to keep in your mind: if I have pure water, glass of water, and if I try to dissolve the haldi, I won't be able to do it. If I cannot dissolve haldi in pure water, how could you expect that I can dissolve it when I can drink it, right? So the bioavailability, it means the amount of the effectiveness of the molecules which is going to treat a particular illness, that is going to happen only when you have the maximum bioavailability. I mean to say that if the bioavailability is higher, only then that problem is going to be cured. Otherwise, it's a problem. So therefore, by drinking any amount of haldi in the form of warm water, in the milk or anything, that is not going to help you unless it is bioavailable for a particular problem, right? So this happens for maximum number of medicines, because most of the medicines which you are taking every day, they are the organic molecules with very tiny ability to be solubilized in the aqueous phase, right? So therefore, most of that medicine is simply drained out of the body. Very tiny amount is going to be used for a particular kind of illness. That problem is being solved when we take the help of the nanoparticle. So therefore, what the nanoparticles are going to do, nanoparticles are usually modified particles. So as I told you here, the colloidal stabilization is in action. So this is a nanoparticle, right? And now this nanoparticle is having colloidal stabilization provided by the colloidal stabilizer in the form of a shell, which is a bilayer, right? So now this particle is a colloidal stabilized particle. So this shell which is there around the nanoparticle is in fact the place where we can put the drug molecules. The drug molecules can be solubilized over here, and nanoparticle works as a carrier. So nanoparticle is taking all the drugs to a place, and it is going to release that. So I mean to say still nanoparticle, right? And the shell, colloidal shell, that is being provided by the colloidal particle to provide the colloidal stability. So that is there. So now at the target site, the drug molecules are released. Drug molecules are released. Now you see that when the nanoparticle is going to release the drug at target, that is highly effective. it is exactly the same way. Rather than drinking the milk with haldi, if you simply sprinkle the haldi on the wound, that would be much more effective. Now, for the external wound, there is no problem. But for the internal wound, how that can happen? This is another way, right? So, this is the way we treat the tumor, cancerous tumor, right? So, you may have the anti-cancerous nanoparticle, or you may have the nanoparticles carrying the anti-cancer drug and simply injecting the nanoparticle over there, and nanoparticle releasing them, and probably it will help. So this is another way of putting the nanoparticle for the biomedical applications. So the main topic of this chapter is the material chemistry at the biointerfaces. We are coming to that point again. But now, after going through different applications that I've shown you over here, right? So the application here, so this was the first one we tried to explain for the shape of the molecule. This was the second, to clean the contaminated water. This is the third one, right? So again, here you need the shape. So I have chosen the spherical particle. You may ask me, why can't I choose the wires of the river? I believe carrying the maximum amount of drug by the spherical particle, that is the most appropriate vehicle that can help me, rather than taking the wires of the drugs, right? So small spherical nanoparticle, they are going to carry a much bigger load in comparison to if I have a sample of the rods of the rivers. So for a particular kind of application. So this was the glamour of nanotechnology in all these applications. As I told you that every medicine has a side effect. The same way nanotechnology, and so that this kind of devices or the techniques, so they are also, or the particles, so they have also the side effect in terms of toxicity. So here we are talking about nanotoxicity. Let me put the drug-loaded nanoparticle and inject in the bloodstream, so that they can reach the target where the drug is going to be released. But the problem is, the carrying medium is the bloodstream, and the bloodstream is not only the aqueous solution as the salt solution, but it has so many other components, like the blood cell, which is a very important component for the survival, right? So now, suppose if I say that these are the nanoparticles, or these are the particles carrying the drug. When they are injected in the bloodstream, that is systemic circulation, these nanoparticles are not expected to break the blood cell. They are not expected to break the blood cell. If on the way they are breaking the blood cell before reaching the target, it means they are reducing the toxicity. So you are not supposed to use such kind of carrying object to deliver the medicine, right? So you need to find out the way that the nanoparticle which you are choosing should not interact with the blood cell membrane. You should keep in your mind that any metallic surface, nanometallic surface, has very high potential to interact with the cell wall. Living cell wall that possesses very high potential. So therefore, the free surface of the nanoparticle has to be passivated so that it should not directly come in contact with the cell wall, right? So you see, these are the coated the nanoparticle. Exactly, this is the coat of the colloidal stabilization. So you should choose the colloidal stabilization by that kind of molecules. Those molecules should not allow the metal surface to interact with the biological surface of the cell wall. And in this way, that is a correct way of using the application. So to avoid the nanotoxicity. So this is the nanotoxicity, so the nanoparticle, if they are, it's not only the bloodstream, because bloodstream is everywhere. The bloodstream is everywhere, no matter if you are going to introduce this in the tumor. So the blood vessels are everywhere, right? So therefore, I mean to say that in order to avoid the toxicity or inducing the hemolysis, this is known as hemolysis. When we break the blood cell, the process is known as hemolysis. So the main objective for the nanoparticle that is going to be used for biomedical application, so the hemolysis must be avoided. So you could see over here, in this image, the nanoparticles are attached to the blood cell, but they are not breaking the blood cell, right? So I also showed you the magnetic nanoparticle for my research. When I use them, so I use specific kind of the sample that is not going to break the blood cell. So this is one example of the nanotoxicity, so you should avoid that. Next one. So this is the nanotoxicity in environment. This is known as the zebrafish. Biology people know it. Very tiny fish, just probably a few centimeters long, and most of it is semi-transparent, right? So this is the normal growth. But if the water in which this zebrafish grows, a contaminated water with the nanoparticle, the growth is not normal. So you could see this is the abnormal growth of the zebrafish in the presence of nanoparticle. So the zebrafish takes up the nanoparticle. I'm not showing those images here. Because the fish, you see now, there's a very common problem of microplastic. So recent studies are saying you are already eating microplastic. Particularly the fish you are eating every day, you may think that that is a freshwater fish. No doubt that is a freshwater fish. But along with the fish, you are eating microplastic. How? Because the fish is not possessing the intelligent mind to differentiate while eating if it's a microplastic or say any other micro living object, right? So therefore, fish is eating everything, right? So it is eating microplastic as well. So once the microplastic is going, that is accumulating inside the fish, and eventually you are catching that fish and eating, and hence you are eating the microplastic as well. So here is the problem. So therefore, our fresh water must be avoided from, or must be cleaned in terms of the contaminant, because eventually whatsoever is the fresh water, that is coming on your food table. So this is the clear example that is not the eating of the contaminant or the nanoparticle by the organisms living in the fresh water or marine water. This is even beyond that, right? So when that is contaminated, the fresh water or the marine water is contaminated, even the growth of the fish is going to be affected. So there is abnormal growth, and the fin fold is straight over here, but it's curved here. There's a cardiac, so cardiac, yolks, sac, and eye, all kinds of organs are showing the deformation with respect to the exposure of the nanoparticle. So therefore, contamination, any kind of nanotoxicity that is existing in the fresh water, eventually affecting the aquatic life. So, what if we have talked about the aquatic life in water? So, what is happening outside with the plant growth? How the plant growth is affected? Again, if your soil is contaminated with nanoparticles. Okay, before going ahead, you might be wondering why the nanoparticles are going to end up in the soil. There are plenty of ways. So now all steel industry, paint industry that is related to the that depends on the metallic paints with small kind of metal particles, you may say, or the mining industry where you have the effluent mining wastewater that contains plenty of those small metallic particles, right? So those small particles eventually they are ending up in the landfill or on the soil or contaminating the freshwater reservoir. So this particular plant growth is the plant growth is being facilitated by biosynergism. So these nodules which are in fact facilitating the plant growth, they are being occupied by the bacteria. So they help in the symbiosis, right? What happens? That bacteria grows in soil, but because of the metal particles' ability to interact with the cell wall, so you see these dots. So these dots are the particles which are there as contaminant into soil. So they are being picked up by the bacterial cell wall, and hence the bacterial growth is affected over here. Thereby, the growth of nodules, so that is affected. Eventually, that is facilitating the nitrogen fixation for the plant growth that is being affected. So, bottom line, the overall growth, suppose if you see this graph, this is the control. This is the control of overall growth of the plant in a non-contaminated soil. But when it is contaminated with the different kinds of carbon nanoparticle, so all these are the carbon nanotube or carbon nanoparticle of different shapes, you would see in all the cases the growth is much retarded in comparison to the control. So you may have the nanoparticle toxicity in water, on soil, or in the bloodstream. There are plenty of implications. So you cannot avoid the nanotoxicity. So therefore you have to find out the way how to passivate the nanotoxicity when you are looking for a particular application. Now, at biointerfaces, you might have seen that I showed this slide, I think yesterday's lecture, when we were talking about regarding the biosurfactants. So, here, how the contaminants in the form of a nanoparticle, they are going to affect your respiratory system. That is also a very prominent example, particularly for the developing country people and particularly in India. When the suspended particle concentration increases in all metropolitan city, in Delhi or other places, and you frequently read the news that the breathing air quality is very dangerous, and the people should take precautions. In fact, what you are breathing, what are the contaminants? Then the suspended particle contaminant. Most of them are the carbon fiber, because when this fossil fuel burns, and therefore the smoke which you are seeing over there, so those particles remain suspended in the air because they are being entrapped by the moisture and all those things, and hence you are breathing them. So apart from that, there are dust particle and all those things. So you may not see them. You see the haze. Most of the time the haze you are seeing, that is being created by the pollutant. It's not a natural process. The mist is the natural process, but the haze most of the time that is being created, that is because of the excessive pollutants or the dust particle in the air combining with that of the moisture, right? And you are breathing them. What they are doing eventually, they are going into the alveolus. These are the particles which are entering into the alveolus along with the inhaled air, where exchange of air is taking place, right? But these particles, what they are doing, they are interacting with the biolayer. So, as you could see that if this particle has the ability that the those amphiphilic molecules, so they can arrange over here and coat them. Exactly, there are plenty of amphiphilic molecules. So this bilayer is made up of amphiphilic molecules, those are known as lipids, right? So when the particle is going to hit this interface, and it can instantaneously grab the amphiphilic molecules. Now there is a constant supply of amphiphilic molecules from the lamellar bodies over there. But when the rate of particle those are hitting the interface exceeds the rate with which the amphiphilic molecules are synthesized by the body, so then that creates a respiratory problem. So it means that this biofilm that is being created by the amphiphilic molecules cannot be regenerated at that space, at that speed by which you are receiving the contaminant, right? So that is the problematic. So I mean to say that the respiratory problem are not alike. As I told you that we have the respiratory problem because of the side effects of the vaccine, COVID vaccine. But what are the respiratory problems in this part of the planet? It is not probably the COVID vaccine that is creating the respiratory problem, but it is the pollution, right? So therefore, this is another form of nanotoxicity. So nanotoxicity working at biointerfaces. So this is the biointerface where the nanotoxicity is working. So it means that what is the solution? Suppose if you ask me what is the solution, you cannot change the amount of the surfactant produced by the human body. It is the same for everybody, right? But you have to control the contaminants, those are being inhaled into your respiratory system. So that is the only way to avoid the pollution. So if you have the clean air, so you can have a healthy lung and healthy breathing system. But if you have a contaminated air at some point, you will be having a respiratory problem. At the end, nanotechnology is a scientific wonder of modern time, but it comes with an indication. You say that I have shown you the applications, but I have also shown you the implications, right? So it comes at a cost, no doubt. No doubt it's a much better way of taking care of the human health. But if you have to take care of the human health by using nanotechnology, you have to be very clear that the nanotoxicity must be avoided. Prevention is the best health cure. Nanoscopic detection is the key to prevention. So I mean to say that because the North American medical system works on the prevention, right? So there we are always under stress. We are being asked every time after a certain amount of period that this test is due for you. You have to go through this test even if you are completely healthy. Here, when we are completely healthy, we don't want to see the face of a doctor, but that is not the case in North America. You have to go to the doctor to go through that particular test because government want that before you tell the government that I am in a critical stage now, and so all the resources the government is going to put to save your life. Before that happens, government wants that there should be a way to detect it, that problem is now coming for you, and there are ways to prevent that problem. So this is the way. So what I have explained today in just a few minutes, we actually our first lecture was on the crystalline phase crystalline solid state. And the reason for that, because the nanoparticle examples which we have taken today, or which we will be taking in the next few lectures, so they all belong to the solid state of crystals. So that's why our focus was that what is the fundamental of crystal structure and how we can understand and differentiate the crystal from that of amorphous. And then it is the crystal that grows in specific shape. In this lecture, so we have placed our attention on the different shapes of the crystal, the shapes of the particle that is produced from by controlling the crystal growth, right? So I mean to say that when you have to use a particular sample of the nanoparticle, so that must possess a same shape of the sample and the same size. Only then you can achieve the results. Otherwise, you won't be having the reproducibility, because the one sample is consisting of maybe more nanorods, nanoribbon, and few nanoparticles. The second one could be otherwise having more number of the spherical particle and less amount of the nanorod and the nanoribbon, and you won't be having the reproducibility. And in this way, you cannot quantify the results. So therefore, in nanotechnology, the quantification of the result is related to the same shape and size of the nanoparticle sample. So therefore, the crystal growth is very, very important. When you have to have the nanoparticle sample, you should have an appropriate methodology available to control the crystal growth. That is much required. Thank you so much for your attention.
Of the nanoparticles, they have a very important role in the properties of nanoparticles. So you have told that the direction of the growth can be controlled by blocking the sites.
Yeah, yes, absolutely.
Affecting planes. So is there any specific mechanism, requirements or conditions that we can control the direction?
Yes. If you know that which direction you have to control and which morphology you have to achieve, obviously by blocking that crystal planes, you can divert the crystal growth in that direction. So you will see that when you have to, particularly for the rod and the wire, it is you have to direct the growth on 110 plane. All other planes must be blocked. Right. So you have to find out the amphiphilic molecules which can be having uniform adsorption. Some will prefer 100 crystal plane, some will prefer 110 crystal plane, and some on 111 crystal plane. So I mean to say that it is all the kind of understanding you need to require, that what kind of amphiphilic molecule those can be absorbed on particular crystal plane, so that you can have a controlled growth. So for the gold nanoparticle, most of the research that is being done in this areas, so that is for the gold nanoparticle. So much easier for the gold nanoparticle to control the crystal growth. And there are many good review articles where they have used many different kinds of amphiphilic molecules, or sometimes even the counter ions for a salt, like bromide, chloride, and iodide. So they can also help in the crystal growth. So it all depends that what are your requirements and in which morphology you want to use. But suppose if you ask me that there is a specified methodology available, I would say no, there is not specified methodology, unfortunately. Yeah, you have to optimize the condition according to your requirement. Any other question?
Flower shaped or a plate shaped nanoparticle. Are they similar or they just give us something? Yes.
They the name of the particle, right? The most of the time, yeah, flower shape or the prismatic shape or all those. So they are the conventional way of just naming them. So whatsoever the kind of shape you are getting, so you will see what is the common name that can be provided. So everybody can understand that. So that is why the flower shape means to come from that direction. Yeah, yeah. What you see and you try to mimic that image with some of the common image, right? So you will try to give the name accordingly. All, yeah, the flower-like structures, them the roughly spherical particle. The word when we use the roughly spherical, you can have rarely entirely a spherical part, but there are very good publication where the people have produced a very precise sphere shapes. In most of the cases, you will see not the precise spheres, but rather roughly spherical, where you cannot make out that if it's exactly sphere or some other kind of a shape is originating. So that is why in most of the cases we use the term roughly spherical. Yeah.
Nanoparticles.
Yeah.
How can we optimize the binding capacity of nanoparticles with drugs? Because all the phenomena depends upon the binding capacity of drug and
Binding capacity or drug loading capacity.
yes.
You want to? Yes, that's a very important question. That is why when uh, you want that this particular kind of a drug you want to release at the target, you need to know or you need to produce the environment that is the favorable environment for the solubilization of the drug. But this is not the required case. So that could be favorable under a different experimental condition. But at when the nanoparticle is going to travel loaded with the drug, then there must be a environment where the drug is going to be released. So I mean to say that the one environment where the binding affinity of the drug is enhanced, so you can load the drug. And so you allow the nanoparticle to travel to a target site, and then you have to create a condition that would allow the minimization of the forces between the molecules which are creating the colloidal stability and the drug molecules. So the drug molecules can be released here. So usually the people do it different kind of experiment. The pH change. So if you have the different pH, the drug molecule. Sometimes temperature variation that can also facilitate that. So uh, I don't know. Apart from the temperature, there could be other change the environment nanoparticle to release the drug. Okay, thank you so much.
Thank you, sir. The next tutorial session will be conducted by Dr. Jaspreet Kaur Rajput on synthesis, characterization and electronic properties of gold and silver nanoparticles in the Department of Chemistry at 2 p.m. Thank you.
today, good afternoon everyone first of all. So today we will talk about the tutorial number 3. So this is related with the synthesis and characterization and electronic properties of gold and the silver nanoparticles. So you people are, especially these students, are excited to synthesize the gold nanoparticles and silver nanoparticles with their own hands. Right, so I think this is also aligned with today's lecture. In the morning you have seen, in the yesterday's lecture you have also seen how the gold and silver nanoparticle can be synthesized in presence of different surfactants, how they are stabilized, how the color changes with the shape and the size, right? So now in today's hands-on experiment training, we will synthesize the gold and silver nanoparticles, and accordingly we can also study the electronic properties. We will study the band gap, how you can calculate the band gap of these nanomaterials through the different techniques. So if I am talking about the gold and silver nanoparticles, first of all, I think you people are familiar with this, that in the morning's lecture also you have studied that what you mean by the nanomaterials, that the size is below 100 nanometer. Broadly we classified those materials as the nanomaterials. So but the question is, why there is a limit of 100 nanometer? Why it's not above or less? So the basic answer to this is related with the, so see, in the first block, if you break it down further and further and further, you can see the surface to volume ratio will change, right? So the surface to volume ratio, it increases so much, surface area to volume ratio increases so much in case when the material is converted into the nano size. So in the nano range, like in 100 nanometers, some materials they, so this is a broad range, 100 nanometer is a broad range, but some materials they show the nanomaterial like properties, the specific properties at 50 nanometer, some show 80, but broadly materials they show different properties than bulk materials below 100 nanometers. So reason is the surface area to the volume ratio, it changes when the size decreases. So the simple example is like, if you talk about the solubility, again it's the surface to volume ratio. If you see the big cube of the sugar or the powdered sugar, then the powdered sugar will have more solubility. It is related with surface area to the volume ratio. So similarly in the nanomaterials, when the size decreases, then surface area per unit volume will also increase. So overall interaction of the material increases when the size changes. So the point is, although there are a number of nanomaterials that can be synthesized and reported in the last decade, but silver and the gold nanoparticles, they have a different class, they are class apart, and they have very significant applications not only in your biological field, but apart from this, it has these particles have great application in the electronics and the optical field also. So these have localized surface plasmon resonance. So because of surface plasmon resonance, this is the resonance occurring, which gives the unique optical properties. So when the size changes, the color of the nanoparticle suspension will also change. So that is because of the surface plasma resonance. And because of these unique properties, these optical properties are unique, so they can be used in the biosensing as a biomarker, right? So biomarker means if you want to sense any bioanalyte in your human body, and imaging and other photothermal applications. So imaging is also related with the spectroscopy, because there is a different color with the different size. So this is more or less related with the optical property of the material, right? So apart from this, there is gold and silver nanoparticle. If I am talking about the bulk material, bulk means which is more than 100 nanometer. The size of the material is more than 100 nanometer, we call it bulk. So if you see silver and gold nanoparticles, these are highly conductive, right? Bulk material is also highly conducting, and when the size changes to nano range, then obviously the conductivity will also enhance, right? So these gold and silver nanoparticles, so these have numerous application in the electrochemical field and the nano devices. And it's not like that we need a large concentration of the gold or the silver. Only a small percentage makes a huge difference, right? So like if I'm making a nano composite, right? So what do you mean by nano composite? It's a mixture of two materials or more than two materials in which one of the phase is in the nano range, right? If my composite contain 1% of nanomaterial, even then it will create a huge difference. So it's not always that we require a large amount of silver or gold, because you know the cost of the silver and gold is very high, right? So they have a chemical stability. Yes, the gold is, you know, the resistant. We wear the gold in the form of jewelry. Why? Because it's resistance to the atmosphere and all. Similarly, silver tarnish a bit, right? But otherwise it is chemically, silver and gold, they are much stable as compared to the other metals. They are not that reactive. And moreover, when we synthesize the gold or silver nanoparticles, we can also stabilize these materials by surface coating, right? The surface properties can be changed by different coatings. So these, further the stability of these materials can be changed. Next. So I have already discussed all the applications in environment science for metal for removal of the pollutant. So in catalysis, gold and silver catalyzed reactions are there, and in electronics, electrochemical, then optical devices, in biosensors and all that, and in biomedicine, right? So gold and silver, they can be used in the medicine. Apart from that, medicine, if you have seen in these days, we are using silver nanoparticles for antibacterial applications also. You have seen there is a washing machine or other microwaves with silver nanotechnology. So what is the silver nanotechnology? It's like antibacterial. You will not have a foul smell, or the bacterial growth will be lesser in that equipment, right? So these are the applications. Next. Now, as far as the synthesis is concerned, there are two pathways. Broadly, there are two pathways. The first one is like top-down approach. Like this is, if you look at the picture, this is the simplest way to explain. If you break a bigger size into the smaller one, that is a top-down approach. And in the morning's lecture, I think you have seen the discussion related to the top-down approach. So, but the disadvantages of the top-down approach is you will not get the uniform size and shape, right? So, uniform size and shape is the main problem in these. But yes, it has advantage. What is the advantage? That we can have a large amount of material at the same time. Right, you can easily crush the material by ball mill or other techniques, and you will get the nanomaterial in a larger quantity. You can get the larger quantity, but the disadvantage is you will not get uniform size in the shape. So this is the disadvantage. But yes, if you want to have a larger amount and the properties are not that much size and shape dependent, you can use this method. But otherwise, the bottom-up approach has more advantages as compared to the top-down. So in the bottom-up approach, the reaction is occurring at the atomic or molecular level. So once the reaction is occurring, then you will have the nucleation process, and in the nucleation process, after the nucleation, you will have a growth, and it will give you the nano clusters, and whatever you are kind crystals, nano clusters. So the molecule, the size of the molecule will enhance. So yes, one nano material or a nano cluster doesn't mean it is a single particle. It will be a combination of more than one nanomaterial depending upon the aggregation, right? So that is why it gives you different size and the shape. If there is only one nanoparticle, single atom, then it will be spherical, right? So why you are getting different shapes? Because once the nucleation is occurring, then the growth starts appearing. So after the completion of the growth, when the reaction completed, you will get the different size. You will get the different size. So this is also, you can say, this is a seed mediated growth. Once the seeding start, then the further growth will occur in that way. So in today's lecture you have seen that you can have variety of shapes of the material. So if I am saying the nanomaterials have different dimensions, so it can range from 0D to 3D, right? So no doubt 3D is not a nanomaterial, because all the 3 dimensions they are in the larger size. But yes, you can have 2D material in which only like nano ribbons, nanotubes, these are 2D materials. Quantum dots are there, right? 0D material in which all the dimensions they are in the nano range. Clear? So in this way, you can synthesize different material of different dimensions, different shape, different sizes. And you have seen in the morning that yes, you can control the direction of the nanomaterial synthesis also, right? Like if you block particular site, then you can increase the growth will only in one direction. So even you can not only the nanorods, you can have flower, star shape. So you have to optimize the procedure, and you can have different shapes. So no doubt the surfactant or the capping agent has a huge role in different size and the shapes. So these are the different methods: the ball milling, laser ablation. So these are the top-down approach methods. Then your sol gel, microchemical, hydrochemical, polyol synthesis, then your condensation method. So these all methods, they are from the bottom-up approach, where the atomic level the reaction is occurring at the atomic or molecular level, and they will continuously giving you the bulk material, right? Mark करें आप? For example, you have a gold, right? So now this gold nanoparticle, once it is formed, right, it can continue to grow like this. It can give you the spherical nanoparticle. And if there is some capping agent, like I am adding this cysteine, this is the amino acid, you know this cysteine. So if this is capped on the gold surface, like gold nanoparticle is there, and there are, if we are using water as a solvent, then we have surface hydroxyl group. So sometimes when we run the IR of the material, you will get the peak of OH group also. So now this OH group is there, so this can give you surface functionalization. Right? So now you can see there is a charged species at the surface. Now the other gold nanoparticle, definitely it will go in this direction. How it will combine now? So you will have interactions over here. This is, so gold nanoparticles, they will combine like this, have a little bit space, and they will orient like this, right? So these interactions will bind the nanoparticle and leads to the growth of the nanoparticles in a particular direction, or they can be spherical also. But this is a growth phase, which is because of the electrostatic interactions. Next is, okay, so we have already discussed this. So applications I have already told you. Now we are coming to the synthesis part, the fabrication of the silver nanoparticles. So now in case of the silver nanoparticle synthesis, we will use the silver nitrate, right? So we will give you the solution of the silver nitrate. We have already prepared the solution. So you need to have 0.25 millimole of silver nitrate, and you know how to calculate the molar solution, right? You know in the first lecture that you have to find out number of moles and how much amount of the volume of the solvent you will use, dissolve, and that will give you the molar solution. Number of moles dissolved per liter of solvent, that is the molarity, right? So here you will have 0.25 millimole of silver nitrate and 0.25 millimole of SDS. And what is SDS? Sodium dodecyl sulfate, right? It's an ionic surfactant that will be used in this case to stabilize the nanoparticle suspension so that the particles can stay stable for the longer period of time. And next one is 0.3 milliliter of cold 0.1 molar sodium borohydride. Now what is the role of sodium borohydride in this case? You have a silver in plus form. In silver nitrate, silver is in plus form, right? So from silver plus to silver you need what? You need a reducing agent. So what is reduction? Gain of electrons. So sodium borohydride will act as a reducing agent. So you need a reducing agent, and the silver plus it will gain 1 electron and it will convert into reduced form silver, right? So now this is a reducing agent, and the product is, you can see this yellow color, it's a mustard yellow color, and this is the yellow brownish mustard yellow color of the silver nanoparticle. So you can see the silver is not always silver. Now it seems golden, right? So this now when you talk about the color coding, then you will say, okay, yellow color of this concentration of nanoparticle, it is yellow. But if you are talking about the bulk, then it will give you silver, right? In chemist language. So next one is the gold nanoparticle synthesis. Now we will use the auric chloride. This is another salt in which we use instead of the silver nitrate, we are using the auric chloride. This is the salt of the gold. So again the same procedure will be there, concentration will be same. Sodium borohydride will again use as a reducing agent, SDS will be there to stabilize the nanoparticle. So instead of SDS you can use the other stabilizing agent. Sodium citrate is there. You can use the other surfactants, the natural surfactants you can use, the saponins, like they are the Rita is there, right? They have saponins as a natural surfactant. So there are number of other surfactants, Gemini surfactants are there, right? So you can use other surfactant also, but this is a basic technique for the synthesis that we are telling you, and further you can look into the literature and you can explore the reaction, and you can further apply your brain and ideas, and you can modify it. So in this case you will see they appear ruby red color, right? So the color of the nanoparticles will be ruby red color. So I think you have seen in today's slide also, in Dr. Bakshi's slide, the ruby red color is because of the spherical nanoparticles, right? So once the particle size is increased, then it slowly and slowly it shifts to the bluish color. So see, the gold is changing so much colors depending upon the size, right? So this is not the new technology. Basically earlier there were no techniques for studying the size of the nanomaterial. We have now sophisticated equipment like electron microscope and XRD and all that, where you can see the size of the nanomaterial. But otherwise the nano exists in the nature quite longer period of time. So if you see the old buildings of certain church or other buildings, so on the glass they have a stained glass. So those stained glass have the suspension of the nanomaterial, because these suspensions are giving different colors. So the painting, the stained glass was made up of different colors of the nanomaterial, like silver and gold and the copper. So different colors are obtained at different concentration and stabilizing agent, right? So that is already existing earlier. If we add this amount in the gold, then we can get this color, and that was used in the painting and all that. But at that time there was no instrument to measure the size and all that. That's why it was not known. And the second thing is, these materials are photoactive, right? So when the glass was there and sunlight was coming, in the presence of sunlight, these materials act, and the bacteria or the other species which are present in that area, because that is a public area, so they have advantage that they are also getting killed, right? So they are photoactive materials. Silver is antibacterial in nature, right? You know that. Copper is also showing these kind of properties. So now you can synthesize gold and silver nanoparticle by these two techniques. Two different salts will be used in this case. The simple procedure is there. Different color is there. You can visually detect the formation easily from the color, right? This is the best characterization technique. You have the sensory system. You can view through the eyes, and apart from this, you can check it through the UV spectroscopy. I am giving the different techniques that can be used for their characterization. Today we will use only UV visible spectroscopy, but I will show you the data, how you interpret the data, XRD, TEM, UV and FTIR. So first of all, in case this is the XRD, and the powder, in this case we use the powder XRD, not the X-ray crystallography. Here we use the powder method. And you know what are the X-rays? The rays which are generated from the target molecule when the high speed electrons, they are bombarding on it. So the transition of the electron is occurring from higher energy shell to the lower energy shell, and they generate the X-rays. So the first Nobel Prize was given for the discovery of X-ray in 1901 by the Röntgen. And this is one of the very important discovery of the science, because the X-rays can pass through the soft tissues but not through the bones. So without surgery, doctors can view the any bone fracture and all the injuries, right? So not only the X-rays are important from our material characterization, but it has biomedical application, lots of biomedical applications. So now the X-ray diffraction method is used here to study the lattice parameters, like you have seen in the morning 111, 101. So what were those? Those were the lattice parameters. So those lattice parameters can be analyzed through the X-ray diffraction method, the phase, the crystallite size. By Debye-Scheurer equation, you can find out the size of nanomaterial through the XR. Okay, so through TEM you can visually see through the TEM micrograph, but yes, through the XRD you can also see the size of the nanomaterial. So this is the XRD of the gold nanoparticle. You can see we have different planes, 111, 200, 220. So this is already reported, and these planes are at different angles. Diffraction peaks are at different diffraction angle. The different angles are there, 38, 44 and 64. So now the point is that how I can check that my gold nanoparticle is formed. So there is JCPDS data, where the crystallographic data is always there, and there is particular JCPDS number, file number, that belongs to that particular crystal, and we normally compare our data with that reported data. So when we compare, we found that these peaks belongs to particularly gold or silver or iron, whatever the metal is there, we can easily compare it with the reported data, right? Next, so this one is for the silver. You can see we have a prominent peak again at 111, 200 and 220. Next. Okay, now UV visible spectroscopy. Today you will see the UV visible spectrophotometer, and you will analyze your synthesized silver and gold nanoparticles by the UV spectroscopy. So now you can see next. This is the UV spectra, UV visible spectra of the gold nanoparticles. So we have plotted this against the wavelength and the absorbance. The absorbance that is shown by our nanomaterials. So we will give you the cuvette. You will add the solution into the cuvette, and then you will run the sample into the UV spectrophotometer, and you will find out this graph. I will show you in the lab course. So you can see there is a wavelength 520 nanometer. So you know this 520 nanometer belongs to the gold nanoparticle. So you have one peak only, not the two peaks. So you have seen that if the different shape is there, like rods are there or wires are there, then you will have again a second peak will be there. But here you will, if you are looking at this spectra, you have one peak only. It shows the particles, they are more or less spherical, or you can say rough surface spherical, right? Next. So this is for the silver nanoparticle. You will have a peak at 400 nanometer in our synthesized method, right? If you use the another method, it may be possible that if you have a different shape, it may be possible you will get another peak also. And yes, with the change in color, the wavelength will also change. Remember this thing, right? So what is the visible range? It is in visible range or not?
Yes, yes.
What is the visible range? 3600 angstrom to 7200 angstrom, right? So this is in the visible range. That is why you are able to see the color, right? 520 and this one at 400 something. Next. So next is the transmission electron microscopy. So here again, that transmission electron microscopy, the fast moving the electrons, they bombarded on the surface of the sample. And why it is called transmission? Because the electrons, they can pass through and you will get the clear image of the substance. Apart from then the SEM microscopy, where there is different secondary electrons, auger electrons, where the electrons are reflected and you get the image from the reflected electrons, we call it SEM. And when the electrons are transmitted through the sample, we call it transmission electron microscopy. So here if you want to see the size, shape, morphology, and if it is having a layered structure, if it has a coating, you can easily find out through the transmission electron microscopy. So this is the TEM image of the nanoparticle. You can see they are more or less spherical in shape, but you can also see they are not agglomerated. They have a space. Why they have a space? Now you can see why they have a space. So right. So if it is coated with some surfactant or some material which provide them stability, so that material is between these two nanomaterials. That is why you can see the space. Otherwise, what will happen? They all will agglomerate and it will give you a bulb size. This is again of the silver nanoparticles, TEM image of the silver nanoparticles. These are from our papers. This is again FTIR of the gold nanoparticles. So now in this case, this is around, if you talk about the nanomaterial, they have a surface functionalization. So in this case, you have a functionalization of sodium dodecyl sulfate. So if it is purely, metal oxide or the metal, then you will not have any peak or this bands in this particular area from 2000, 3000, right? It will be below 1000 if it is metal oxide or the metals. But in this case, all these peaks are because of the surface coating with the organic moiety. You have a sodium dodecyl sulfate. So you can see that there are different CH2 bending, different type of vibrations are there, then sulfate is there. So these peaks related to the surface coating of the surfactants which are which have organic moieties, and that is why you have the peaks of all these, and it shows that coating is there. Similarly, again in this case. So next one is the electronic properties. So why they show different electronic properties? They have better electrical conductivity. Now the conductivity, it also depends upon the band gap. Band gap is the gap of the energy between the conduction and the valence band, right? So if it varies, then the band gap will also vary. So if the size of the nanoparticle change, the band gap will also change, right? So the electrical properties, they are more or less based upon the band gap. And again, the surface plasmon resonance, they will decide the optical properties. So sometimes the optical properties can be aligned with the electrical output, and you can sense the material, and this technique is used in the biosensing of the material. So obviously I have told that silver and gold, they have a better chemical stability as compared to the other metals. Although they are costly, because of this particular feature they are used in the various nanomaterial synthesis. And yes, quantum size effect, if the size can be reduced below 10 nanometer, we can say they have a quantum effects also. Catalytic properties and charge transfer is also possible in case of these. So I have already told you this band gap. So you can see the valence band and the conduction band. If you decrease the size, then this will show a semiconductor like behavior. The band gap will change. Next. So yes, you can find out the band gap through the TOS equation. So this TOS plot can be derived from the UV spectra. From the UV spectra, you can find out there is a Lambert-Beer law, right? So from the Lambert-Beer law, you can find the absorption coefficient, and using that absorption coefficient, you can find out the band gap very easily. So Eg is the band gap, h nu is the energy for the transition, A is the absorption, and your alpha is the absorption coefficient, and n is the transition. So when we draw the plot for this TOS plot, you can extrapolate this, and you can find out the value of Eg is 1.83 in this gold, and in this our silver nanoparticle it is 2.79 electron. So yes, you can find out the size from the XRD plot also. So in case of the XRD, there is a Debye-Scherrer equation. So you can find out the size through Debye-Scherrer equation also. The K is the constant, Scherrer constant, the value is 0.9. And lambda, this is the wavelength of the target. Normally we use copper in this case, 1.54 Angston is the value. So copper is normally used as a target, but if you change the target, the wavelength can change. But mostly the when we characterize a nanomaterial, they use the copper K alpha as a source or as a target of the X-rays. So next is the beta, and then is the cos theta. So what is the beta? Beta is the full width half maxima. So if you have the plot of the, like this is the X-ray plot. So what is this? This one is full width. This one is full width, and the half. This one is the half of this peak, and this half will give you full width half maxima. And the value of this full width half maxima will be this cos theta, the angle which is there, angle of diffraction which is there, and from this you can find out the crystallite size of the nanometer by using the XRD. You can compare the data of the XRD via TEM analysis also. So you can compare both and can find out what is the average crystallite size of your nanometer. Okay, so now I am concluding that today you will synthesize. I have given you the instructions and the brief introduction about the silver and gold nanoparticles. What are the possible method of their synthesis? How you can manipulate the different methodologies according to your need, and what are the different characterization techniques. So apart from these, there are other characterization techniques, but these are the basic ones which are really necessary. You can have other information also related to these nanomaterials. So UV you can run today, and you will see where the absorption will be there in your particular synthesized nanomaterials. Okay, so again top plots you can draw by yourself. and from that UV data you can draw the top plot and you can find out what is the band gap of your material, right? So if you have any query, okay. So shall we start with the hands-on? Okay. Salsa, a silver nanoparticle and gold nanoparticle. So we have already synthesized the silver nanoparticles, and you can see this is quite stable, and they are not settling the sizes. It is molecule and precipitate of this and out. You can see what is the this one is gold. What is the cost? Right? Right? You can use this suspension in nanocomposite synthesis also. Right? You can add the bulk material to your these nanomaterials, and so you can have different applications. Like you can use it in photocatalysis, and obviously the stamping is also there, and as a catalyst also, a variety of applications are there. So I've already told you in the morning, you can read the research papers and so you can take the solutions from here. You can do one by one, group-wise you can start the synthesis. Silver and yellow color.
बंदूक कितना अच्छा है हाँ लोग सेंटर में
पूछ ले
यहाँ पे नहीं था वो कल नहीं अभी भी अच्छा वो कर वो इसका भी ड्राइवर कल हाँ हाँ प्लान में है स्क्रू ड्राइव, अभी स्क्रू ड्राइव होगा इस प्लान में याद नहीं आता। तो वैसे मेरे हाथ से थोड़े से वो हटाए थे ना तो उसके तो थोड़ा रिस्की है। लैपटॉप पर भी चेक करेंगे तो आपको टिक शो कर देगी ना कि कहाँ कहाँ आपकी टिक आ रही है। थोड़ा सा लेफ्ट में घूम सकते हैं। चेक टिक का ठीक है ना, आपकी टिक कितने का 560 ठीक है ना। तो क्या हो गया इसका मतलब आपके गोल्ड नैनो पार्टिकल्स ठीक है, ओके। तो बाकी सिल्वर वाले को करते हैं। ठीक है, करो, क्या करो, निकालो कीबोर्ड निकालो। इसको
एक एक करके ग्रुप वाइज ही आओ ना, अभी एक एक करके
एक ग्रुप
कुछ टीचर्स भी है ना।
आप लोग आ जाना अभी हाँ, थोड़ा और थोड़ा रेस कर मुझे ना। अब से स्टार्ट करते हैं। क्या कहते हैं कैपेसिटी आपकी स्टार्टिंग है 8 मिनट से एंड टेम्परेचर 5 मिनट एंड इंटरवल 1 हम स्टार्ट करते हैं। वाला है ना 400 के अराउंड ही जा रहा है।
So you have exercise? You can take that.
आपकी ना इंटेंसिटी ज़्यादा होगी, कंसंट्रेशन ज़्यादा होगी ना, इसलिए इंटेंसिटी ज़्यादा होगी। और इंटेंसिटी है वो 1 के आसपास है, तो उसमें एरर के चांसेस कम हैं।
You can put your group number. You can add the group number and simultaneously the UV is also there. You can see the peak at around 400 is there, right? So this belongs to the silver nanoparticle. Silver nanoparticle. Screen पे कर. बस ठीक. So now you can see the UV plot. Hurry up, come here. So So now this is the UV spectrophotometer. You can see this equipment. So we are adding the cuvette full of your sample. So cuvette is added of this silver nanoparticle. We have prepared this silver nanoparticle, yellow colored solution. So now the sample is kept inside this UV visible spectrophotometer, and the analysis, the UV plot of the sample is here. The peak is occurring at around 395 nanometer, closer to 400 nanometer. So this is the peak. So if there is a shift in the peak, either it can be bathochromic, or it can be redshift, or it can be blue shift, right? So if it is toward the higher wavelength, we call it redshift. If it is toward lower, it is called blue shift. So as the size changes, the shift can occur from this side to this side. So now you can carry out your own spectra. Now this one is particularly for the silver. So next we will run for the gold nanoparticle. You can take the picture, and from these values you can draw the top plot. From the Lambert equation you can find out the value of alpha, the absorption coefficient, and using the absorption coefficient you will derive the top plot, and from top plot you will get the band. So you will do the calculations now after this UV spectra. So every group will carried out this UV spectra for his or her own sample. So this one is the UV cuvette. You can see this is the UV cuvette. This is okay. So you can put the sample in this. You have the black sample. So already we have the sample, black sample, which is containing water. So it is there, and now this is a test sample. So now the gold one. So you can get back the sample, because there is no effect of this UV on your sample. It will not decompose, right? So this will not disintegrate your sample. You can use it again. So you can get the sample back from the cuvette in your vial. इधर भी कर दो बच्चों, विक्रांत को कर दो, स्टूडेंट्स। So now you can see, you will get the data. can take the image of your plot also. So 516, I have told you 520 nanometer. So this is approximately same 516 nanometer. So earlier it was 516 nanometer. So now you can see this broadband is there. So why you get broadband in the UV spectrum? Why not the sharp one? Have you seen all UV spectra? In the other one also. So UV spectroscopy is electronic spectroscopy. So here the transition of electron is occurring from one energy level to the another energy level. So the point is each electronic level has a number of another levels: vibrational energy level, rotational energy level, right? So the transition of the electron can occur from one vibrational to other, one rotational to other. So large number of transitions are there in the this electron spectroscopy, UV spectroscopy. That is why each transition contribute and you get a band, broad band in the spectrum, right? Because each and every transition is contributing. So transition of lower energy in this area and higher energy in this area. So everything is contributing, which gives a broad band in the UV spectrum. So now you can see the peak is easily visible around 516 nanometer. So now it is confirmed you have synthesized the gold nanoparticle. Other group has the other previous spectra was of silver nanoparticle, which was around 396, right? So now the next group will also carried out, and in the meantime you will plot the top plot, and from that you can calculate the band. So carry out one by one, group wise you can draw the spectra.
अच्छे से करवाते हैं ना ये बच्चों प्राइवेट में थोड़ा करवाते हैं
put our solvent in this liquid and your sample in this liquid. Okay. Now we will start. This is your silver or blue? Silver. So here it will give a peak at around 400. Actually, it is low, but it's accurate. Okay, I'm seeing like nearly all students are getting their value around 568. So it means like it's versatile, like give the same value again, accurate. Okay. नीचे वाले लैब में यूनिट में कभी भी ऊपर वाले लैब में फ्लोरो करने जाओ ना, कभी 10 कम दिखा देगा, कभी ज़्यादा दिखा देगा। उसमें प्रॉब्लम वो फास्ट है ना। आपका सिल्वर का 395 के अराउंड आएगा, सबका तो इतना ही आ रहा है। Now click on this check key after the spectra list. Check key. See, it's 390. Okay, you can click picture. Take out the liquid and take your sample and then hold it.
Forward.
want to try? Ma'am?
Have you calculated the tau value? So you can keep the sample and store it, or you can submit it to our team. So on the last tutorial you will use these samples for the removal of this silver and the gold from the aqua solution. So now we will remove the heavy metal by synthesis of the iron oxide. So this one is 395 and 560. Submit the sample. Take the sample. Okay? Okay, you can keep it in the report. So you have the same value? 569, 400 or 393. So you can keep the sample in your area. What is the value of UV? 390 for the silver nanoparticle and around 560 for the gold one. So the color is perfect. Keep it the bluish or black, right? It means we are the stable. Now can you see the suspended particle? What are these suspended particles? These are the fibers of tissue. Right? So that is why when we are working in the material, we show it in this place of the figure. And you see that figure it is the tissue paper. So how many groups? Or everyone has completed? Yes. So now I am winding up. So all the groups have completely synthesized the silver and the gold nanoparticles. Yes. Everybody. So we have two different samples, one of the silver and other of the gold. Can you show me the samples? spectrophotometer, and using that data you can draw the top plot. We have the original software, and through this software you can put the values and you can draw the top plot, and further you can get the band. So these are the silver and your gold nanoparticles. So please preserve these in your Almira. So day after tomorrow, when you have the 5th tutorial, you will use these nanoparticles for the separation of these nanoparticles from the aqueous here, right, from the aqueous solution by using the iron oxide nanoparticles. So here the silver and the gold nanoparticles, they will act as a pollutant, or you can say the heavy metal in water. So you can clear the water. Similarly, here in this in future's experiment, you can purify the water, remove the contaminants from the water with the use of nanoparticles, iron oxide, surface active iron oxide nanoparticles. And similarly, you can use these nanoparticles for the other applications, for the biosensing, optical sensors, electrochemical sensing, or you can synthesize the nanocomposites. So you can read more research papers, get more ideas for their applications. Okay. So keep this sample and store it. We will use it. Okay. So now the synthesis you have done, the characterization you have done with the UV spectroscopy. Take the data, and now you can plot the top plot and get the value of the band. Okay, so now the tutorial is finished. You have completely understood how the compound iron, silver and gold nanoparticles, they are formed by the wet chemical synthesis, by solution synthesis, and how you can characterize easily in your lab. Further, if you want to analyze for the XRD or you by TEM, then you have to go for that characterization. And you can get the size of the nanoparticles by transmission electron microscope. And there are other techniques also where you, for example, if you are synthesizing iron oxide nanoparticle, then for a magnetic material you have to find their magnetic properties. So BSM analysis or squared analysis can be carried out to study the magnetic properties of those materials. So that is not for the silver and gold nanoparticle. That is for magnetic material, like iron oxide is there, or copper ferrite is there, any ferrite, copper, cobalt, nickel ferrite, or you can have other materials like perovskite material like bismuth ferrite, BiFeO3 type compound. There are different variety of magnetic materials. Iron oxide is not the only one, right? That we will do in the next lectures and tutorial. So thank you. If you have any questions, you can ask.